welcome to this course of building Agentic RAG applications. So initially, we will understand what is an agent. So an agent is an AI assistant that uses a large language model along with the tools to complete tasks. In an agentic workflow, one or more agents can work together to manage and perform tasks. Now moving on, we know how does it work. So the first one is its understanding and action. First, the agent uses its language skills to understand your question. Then it decides which extra tools it needs to use to get the job done. The next is task management. In many systems, one agent can work together with other specialized agents. Think of it as a team where each member has a specific job. Let's see an example. Imagine you want to translate a document into several languages. The main agent is the first step. So a main agent receives your request and breaks down the translation task. Then come specialized agents. It then assigns parts of the work to other agents, each of which is specialized in a specific language. Then is collaboration. These agents work together and then send all the translated parts back to the main agent, who puts everything together for you. In short, an agent is more than just a part of an AI. It's an active helper that uses its own intelligence along the extra tools to manage and complete various tasks, often by working as a team with other agents. Now we will understand what is RAG. So RAG stands for Retrieval-Augmented Generation. It is a method that helps AI get more accurate answers by using the external knowledge sources. It combines information retrieval with the AI-generated responses, allowing AI to access and use the real-world data. With RAG, AI doesn't really rely on its built-in knowledge. It looks up relevant information from a database or documents before answering. These knowledge sources can be structured databases like SQL or Postgres, or unstructured ones like the PDFs stored in the vector databases. This helps AI provide more accurate and up-to-date responses. Now moving on, let's understand what is Agentic RAG and why it is even so useful. So instead of relying solely on a single language model to generate answers, Agentic RAG turns these models into smart AI agents. Each agent can use the additional tools, functions, and the external knowledge sources to complete the task. In an agentic system, several agents can work together. For instance, one agent might be in charge of handling data retrieval while another focuses on progressing and generating languages. They effectively form a team where each member has a specialized role. Now moving on, we'll understand why Agentic RAG is useful. It is useful because of its better problem solving. By distributing tasks among specialized agents, Agentic RAG can handle more complex and nuanced problems than a single language model might manage on its own. Then moving on, we have tool integration. Each agent is not limited to just one programming language processing. It can use extra tools like search functions, databases, or the specific APIs to get more accurate and detailed information. For example, in a tax-related system, one agent could focus on creating tax cards, another could handle managing tax collections and returns. A third could deal with translating the tax queries into different languages like the Swedish or Spanish. Now moving on to the next one, we have flexibility and efficiency. So this system adapts to various tasks by assigning them to agents best suited for the job. The collaborative structure means that even if a problem is multifaceted, each part is managed by the most capable agent, leading to more efficient and effective results. Think of Agentic RAG as a team of expert assistants. Instead of one person trying to do everything, each assistant is specialized. They share information, use extra tools, and work together to provide a complete solution, even for the complicated problems. This makes the overall system much more powerful and versatile in solving the real-world issues. Now moving on, let's understand what are the components of the Agentic RAG. So Agentic RAG has 4 key parts that work together to find, enhance, and generate information. So the first one is prompt. So what it is? The prompt is the question or the instruction you provide to the AI. So in simple terms, it's like asking a question or giving a command to start a conversation. So why does it even matter? It matters because the prompt sets the context for what the AI needs to do, guiding the whole process. Then moving on, we have the large language model. So the large language model is a core AI engine that understands your prompt and generates a response. So in simple words, think of it as a very smart text processor that has learned from the lots of examples. It uses its trainings and language skills to create an answer that fits your request. Now, the third one is agent. So the agent is an AI assistant that works alongside the large language model. So in simple terms, it's like a helper that knows how to use the extra tools to find more detailed or specific information. So the agent fetches the right data from the various sources to ensure the answer is complete and accurate. Now moving on to the fourth one is knowledge base. The knowledge base is a storage system for different types of information. In simple terms, imagine it as a big digital library that holds structured data organized like a database, for example, tables. Semi-structured data, for example, organized in a less rigid format like the spreadsheets or JSON. It can also be unstructured data that is raw information like the text documents, articles, or even emails. So it provides the content and the facts that the AI can draw on to answer your prompt accurately. Together, these four parts work like a team. You ask a question or give a prompt, the LLM thinks of an answer, the agent gathers any extra details needed, and the knowledge base supplies all the relevant information. So now the question comes, why do we even need RAG agents and what do they solve? So the traditional RAG systems have knowledge gaps because they can't access multiple knowledge sources. By adding AI agents, these gaps can be filled using the external tools. If the AI doesn't know an answer, it can effectively fetch data from external databases and reliable sources to respond accurately. So using multiple knowledge bases and AI agents helps in several ways. For example, it helps in reducing mistakes. So AI can compare different sources, making answers more reliable. Then moving on, it is important for better understanding. So accessing diverse knowledge helps AI answer complex questions more accurately. Now, it is scalable. The system can handle large amounts of data and serve millions of users efficiently. So this approach makes AI-powered applications smarter, more reliable, and capable of handling the complex queries. So down the line, we'll see a lesson about the router query engine. So let's move on. So let us understand what is a router. So the router is the simplest form of an agentic Retrieval-Augmented Generation, that is RAG system. It is responsible for directing user queries to the appropriate retriever or response module based on the predefined logic. Then the question comes, how router works in Agentic RAG? So initially it receives the query. It takes the user input or the prompt. Secondly, it classifies the intent, that is, it identifies whether the query requires factual retrieval, summarization, or generative response. Then it routes to the right system, that is, it sends the query. It sends the query to a knowledge-based retriever for factual lookup. It can even send to a specialized large language model for generation if creative or open-ended. It can even send to a combination of both for hybrid responses. Now, let's see all this in action. So regarding the OpenAI API pricing, you can go directly to this openai.com API pricing wala website, and then when you scroll down, you will see and explore the detailed pricing, and you go there and you will basically find all the latest models with the input, the cached input, and the output as well. So in this course, we are using the GPT 3.5 Turbo, and its input is $3 and the training is $8. And if you contact the pricing, you will see it cost $0.5 and the output is $1.50. So basically, you can take up any API that suits well in your project. So the first thing we do is to import our OpenAI key, and to do this, we will use a helper function. So let's run this. Next, we run this nest Asyncio module because Jupyter runs event loop behind scenes, and a lot of modules use async, and to make async play nice with Jupyter Notebook, we need to import this. So let's run. So the next step is the setup is to load the document. So here we are using the Meta GPT, a recently accepted oral paper, Clear 2024, on a new multi-page framework. So we are loading the documents over here, and let's run this. You can run this by even pressing Shift plus Enter. So after we have completed with loading the documents, we will need to import the sentence splitter from Llama Index. So we have even mentioned the chunk size over here, and we are splitting the documents. So this step is optional, and this allows to find an outline and embedding model. And you can do this by specifying a global config setting where you specify the alignment and the embedding model, and that you inject as part of the global configuration. So by default, we use the 3.5 turbo and the text embedding 202 in this course. So this allows you to have the groundwork to basically inject your own large language models and embeddings. So here we are importing settings, we are importing OpenAI, and we are even importing the embedding of OpenAI. We're using the GPT 3.5 Turbo as we have discussed, and we are building on text embedding. So now here we will set up both the summary and the vector index. It's nothing, just we are importing the two simple modules, the summary index and the vector store index, and we are initializing this. Now it's time to turn these indexes into query engines and then query tools. So each query engine represents the overall query interface over the data that's stored in this index and combines the retrieval with the LLM synthesis. So each query engine is good for a certain type of question, and this is a great use case for the router, which can route dynamically between these query entrants. So a query tool is just a query engine with metadata, specifically a description of what type of question the tool can answer. So let's run this. So here in this code, we define the summary query engine that equals the summary indexed as query engine, and then also a vector query engine equals the vector index. We can even see that the vector query engine is derived from each of the index. So we will see that for the summary query engine, here the summary query engine, it is also the same. So let's run this. So here basically we are defining the router query engine, and we are importing the router query engine from Llama Index Core query engine router, and then we are initializing the query engine is equal to router query engine. So we have selected the LLMS single selector from the defaults, and we are using the summary tool and the vector tool that we have built previously, and verbose is equal to 2. So then let's run this. So let's ask a question to the query engine that what is the summary of the document, and then we'll print the response, print str and then response. Okay, so let's run this. So see, it is given the response. The document introduces MetaGPT, a meta programming or framework that enhances the problem solving. It is basically a summary of the MetaGPT document that we have used. So then let's see the length of the response source. So we'll write print length as usual. In the previously we have also seen this, how to write response dot source nodes, and we will run this. So let's see, it's 34. So we have another question ready for the query engine to ask, and we will run this, and then we'll print the response, print str response, and let's run this. So our question was, how do agents share information with other agents? So agents share information with other agents by utilizing a shared message pool where they can publish structured messages and also subscribe to relevant messages based on their profiles. And it has given the correct answer. So let's Now put everything together and we are importing this get router query engine and we are passing this MetaGPT PDF as before and we will run this. And now we have one question to ask is tell me about the ablation study results. So we will run this and we will now print the response. Print str, then again response. So the ablation study results show the MetaGPT effectively addresses challenges related to the context utilization, code hallux and everything. So this is what about the query engine router, and down the line we will see about tool calling. We will discuss how to use an LLM to not only pick up a function to execute but also infer an argument to pass through the function. So let's move on. We will discuss how to use an LLM to not only pick up a function to execute but also infer an argument to pass through the function. So when building Agentic Retrieval-Augmented Generation, that is RAG applications, tool calling plays a critical role in enabling agents to retrieve, process and generate responses effectively. In this context, the tool calling refers to an agent's ability to invoke external tools, APIs, or databases dynamically to enhance its decision making and the response generation. So in a nutshell, the tool calling allows AI agents in our RAG's pipeline to fetch external data, that is from the web search, databases or APIs. Then it processes the structured information, that is running calculations, querying vector stores and etc. Then interact with other systems, for example calling Python functions, SQL queries or the cloud services. Then it validates responses before generating the final answers. So this ability arguments the model's capabilities beyond what is stored in its training data, making it more adaptive and accurate. Now let us understand how tool calling works in the RAG applications. So a multi-agent RAG can be structured where different agents have specialized roles and tool calling allows them to interact with different sources of knowledge dynamically. So the steps in the typical agentic RAG pipeline with tool calling are as follows. The first one is user query processing. So the pipeline begins when the user submits a query. The system first analyzes the intent and context of the query to determine if additional external information is required. At this stage, the agent decides whether the query can be answered using the model's internal knowledge or if the external data sources such as APIs or databases need to be consulted. So if the query requires real-time data, structured information or enhanced retrieval, the system prepares for the external tool calls. So additionally, the agent may reformat the query to optimize retrieval, such as converting a natural language question into a structured SQL query or search command. So if no external retrieval is needed, the system proceeds to generate a response directly from the language model. Lastly, second, we have the retrieval and the augmentation. So if external data is required, the system selects the most appropriate retrieval mechanism. One of the primary approaches is semantic search through the vector databases like the Pinecone or the FAS or the Vivative, which helps locate the most relevant documents based on embeddings. If structured data is necessary, such as financial reports or customer details, the agent constructs and executes the SQL or the NoSQL queries against the database or the knowledge graph. So when real-time information is needed, such as weather updates, stock prices or the recent news, the agent makes API calls to external sources like the OpenWeather, Google Search or other LangChain tools. Additionally, retrievers from frameworks like LangChain can fetch knowledge base entries, FAQs or reference documents. Once relevant information is retrieved, it is appended to the query, augmenting the model's context for improved response accuracy. Now moving on to the third step, we have processing and validation. Once the retrieval process is complete, the system processes the obtained data to ensure its accuracy and relevance before using it in the final response. So if multiple documents or data points are retrieved, the system ranks them based on the relevance and may apply summarization techniques to condense large amounts of text into digestible insights. In cases where numerical calculations or complex logical reasoning are required, the agent may execute Python functions to compute the required values. For example, if a user asks what is 15% of $1,200, the system calls a function to perform the calculation. Additionally, when fetching the real-time information such as the stock prices or the news update, the system verifies the timestamps to ensure the response reflects the most recent data available. If redundant or conflicting information is retrieved from the multiple sources, the system filters and deduplicates the content before proceeding. Now moving on to the fourth step, we have the final response generation. So once the information has been processed and validated, the system generates the final response. That is, the language model integrates its internal knowledge with the retrieved and the computed data to produce a coherent, well-structured answer. The response is formatted in a user-friendly manner, ensuring clarity and consciousness. If multiple sources provide different insights, the agent may cite references or present multiple perspectives. The system also refines the language to enhance readability, simplifying complex data if needed. If the user requires further details, a feedback loop may be initiated, allowing for query refinements or additional retrieval. By intelligently synthesizing all available information, the system delivers an accurate and context-aware response. So this structured pipeline ensures that an agentic RAG system effectively determines when and how to retrieve external knowledge, process information, and generate reliable responses. Tool calling significantly enhances AI capabilities by allowing it to access real-time data, execute computations, and validate information dynamically. As a result, the system becomes more autonomous, context-aware, and capable of handling complex, information-rich queries across various domains, including the research, customer support, and business intelligence. Now, let us see everything in action. So, initially we will begin with the setting of the API key. Then we will run this. So now, after we have set up the OpenAPI key, it's now time to set up and import our Nest Agentic IO model, and we will run this. So next, here we will give you a basic understanding of the tool calling. We will show you how to find out a tool interface from a Python function, and the large language model will automatically infer the parameters from the signatures of the Python function using llama index abstractions. To elaborate this, let's first define two toy calculator functions and show how tool calling actually works. So we will define an add function and also a mystery function. The core abstraction in the llama index is the function tool. So this function wraps any given Python function to feed it. And you can see that the function takes both the add functions defined here as well as the mystery function, which is just x plus y times x plus y. Here, you can see that both the add and the mystery functions have type annotations for x and y variables, as well as the docstring. So, it also integrates natively with the function calling capabilities of many of the large language models, including the OpenAI. To pass these tools to an LLM, you have to interpret and import the LLM module and then call and predict. So, this code imports the OpenAI module explicitly, and you can see the module is 3.5 turbo. And then we can call the predict and call function on the top of the large language model. So what predict and the call does this, they take a set of tools as well as the input prompt series of chat messages. And then it's able to both make a decision of the tool to call as well as call the tool itself and get back the final response. So let's see the output. Print str response. And we'll see the. So here we see the intermediate steps calling function here with arguments. You know, x equals 2, y equals 9. So we can see that at least I call the right tools and also infer the right parameters, and the output is 1 to 1 and is 11 times 11 is 1 to 1. So we get back the right answer. So here after running this, we will use the same paper's MetaGPT as before, and here we'll pay attention to the chunks. We will use llama index and the sentence splitter as before to split these documents with the chunk size is almost equal to 1024. So let's run this. So here you can see that the chunk size is mentioned as 1024 and we are using one sentence splitter as planned, and we'll run this. Here, each node here represents a chunk. So let's take a look at the content of the first chunk. So we can print the content by the node.getContent, and here we want all the metadata attached with the content. So that's what metadata mode is equal to all. So let's run this and we get the output. We not only got back a parse representation of the front page of the paper, we can also see the metadata attached at the very top. So this includes the page label equal to 1. It also includes the file name, file path, the PDF file, the file size, and credit and dates. We will put special attention to the page levels because for instance, if we go in and try out a different node, we can see that it will return a different page number. So let's see. So next we are defining a vector store index over these nodes. This will build the RAG indexing pipeline over these nodes. It will add an embedding for each node and it will get back a query node. So basically we can actually try querying this RAG pipeline via metadata filters just to show you how metadata filters work. So here we are importing the metadata filters and then we specify a filter where the page level is equal to 2 and then we have a query. So what are some high level results of MetaGPT? Then let's run this and take a look at the response. So we'll again do print str response. So MetaGPT achieves a new state-of-the-art in code generation benchmarks with 85.9% and 87.7% in the pass at the rate 1, surpassing other popular frameworks like AutoGPT, LangChain, and it has given the right answer. So after we have this response printed, we can iterate to the source nodes. We can actually print out the metadata attached to these source nodes, and I'm very curious. So let's run this. So the file path, the file type, the file size, creation date, and the last modified date, everything is given. So this is awesome. So here we will define the Python function that encapsulates this. So it has given the key page level value p in the page numbers. We have even initialized the query engine, created a vector index, and then we want a return response. Then we have even initialized the vector query tool. So we will define a function called the vector query, which takes in the query as well as the page numbers. It allows us to perform a vector search over an index basically. So we'll run this. So let's try calling this tool with an LLM, specifically 3.5 Turbo GPT. We do product and call on the vector query tool and ask the same question, high level results of MetaGPT as page 2. So we'll run this. And as an output, it's a calling function vector tool with arguments query high level, and we will print the response of the source nodes as well as the metadata. So as before, we will verify the source nodes and we see that the page level of the source nodes, there is one source node return and it has a page level of 2. So we'll move on and create the summary index. So here we are importing the summary index from the Llama index core importing query engine tool, and basically we are building one small other tools. So finally we can bring in the summary tool from the router. Example, in the first lesson we have already passed it, and we can combine that with the vector tool to create other tools. So now let's try calling the tool again. We asked for what our comparisons with chapter 5 on page 8. So we see that It calls a vector tool actually with page number equal to 8 and is able to still give the right answer maybe. Yeah, it has given the right answer. So now we can verify by printing out the metadata and of the source nodes. So let's run this. So it is given a page level of 8, file name and all the details necessary for verifying. So lastly, we can ask a question like, what is the summary of the paper? To prove that, LLM can still pick the summary tool while necessary. So it can actually still give the right answer. So down the line, we'll see how to build an agent reasoning loop, and let's move on. Now let's see the two key important components of an agent. So the first is agent task orchestrator. So the task orchestrator acts like the conductor of an orchestra, ensuring that every part of the system plays its role at the right time and in harmony. So here is how it functions. It acts as a central coordinator. It manages the overall flow of the task within the agent. Just as a project manager assigns work to the team members, the orchestrator assigns tasks to different parts of the system. The next comes scheduling and prioritizing. It determines the order in which the task should be performed. Tasks may be queued based on importance, deadlines, or dependencies. This helps in handling multiple tasks efficiently without causing delays or conflicts. So, secondly, the thing is resource management. It keeps track of the system resources like processing, power, and memory and allocates them to the task as needed. By doing so, it ensures that each task gets the necessary resources to execute properly. Next comes task monitoring. The orchestrator monitors the progress of the task in real time. It detects any issues or delays and can reassign or adjust tasks to maintain the smooth operations. This monitoring helps in quickly identifying the bottlenecks or the failures. Now moving on, we have coordination among subsystems. In complex systems, multiple subsystems might be involved. The orchestrator ensures that communication and data exchange between these subsystems occur seamlessly. It manages dependencies between tasks so that the one task output is correctly passed as input to another. Now moving on, we have error handling and recovery. If a task fails or encounters an error, the orchestrator can trigger corrective measures. It may reschedule tasks or notify other parts of the system to take over, ensuring reliability and robustness. Now moving on, the second key important component is task reasoning and execution. This component is where the actual thinking and the doing happen. It is responsible for making decisions and performing the actions necessary to complete a task. So, the first one is task analysis and understanding. It starts by breaking down a complex task into smaller, more manageable steps. The module analyzes the requirements and context of the task, much like planning out steps to solve a problem. Now moving on, we have decision making. Using built-in logic and reasoning algorithms, it decides on the best course of action. This may involve evaluating different strategies or paths to determine which is more efficient or effective. It can adapt based on new data or changes in the environment. Now moving on, we have action execution. Once a plan is in place, the module carries out the necessary actions. This involves directly interfacing with hardware, software, or external systems to perform the task. The execution is dynamic, meaning the module can adjust actions in real time if unexpected issues arise. Now moving on, we have feedback logo. After performing actions, it gathers feedback on the results. This feedback is used to refine the future decisions and improve the task handling. Continuous learning from successes and failures is a key feature over here. Now moving on, we have integration with the orchestrator. While the orchestrator assigns and monitors tasks, the reasoning and execution component does the actual work. The two components work in tandem. The orchestrator provides the task and the reasoning module processes and completes them. This collaboration ensures that the agent operates both intelligently through reasoning and efficiently through coordinated execution. So together, these two components empower an agent to perform complex tasks reliably and intelligently. The orchestrator ensures that everything runs smoothly, while the reasoning and the execution model handles the actual problem solving and the action taking, making the agent both organized and smart in its own operations. So after we know all these, let's understand about controlling an agent. So let's see, what does controlling an agent mean? So it means guiding the behavior. It means directing and managing how an agent, like a smart robot or a software program, acts in different situations. The second one is setting goals. You establish clear objectives and rules for the agent to follow. Now moving on to the third one, we have monitoring actions. You keep an eye on what the agent does to ensure it stays on track. Now let us see why controlling an agent is so important. It is important because of the safety. It prevents the agent from taking harmful or unattended actions. Then comes reliability. It ensures the agent consistently performs its task correctly. Then comes efficiency. It helps the agent adapt and improve by providing feedback and adjustments. Now moving on, we have alignment. Make sure the agent's actions match the desired goal or task. So this process of controlling an agent is crucial for maintaining order, safety, and efficiency in systems that operate autonomously. So now let's see all this in action and in practical. So far, our queries have been done in a single forward pass. Given the query, call the right tool with the right parameters and getting back the response. So what if the user asks a complex question consisting of multiple steps or a question that needs to be answered in detail? So in this lesson, you will learn how to define a complete agent reasoning loop. Instead of the tool calling in a single short setting, an agent is able to reason over tools and multiple steps. You will use the function calling agent implementation, which is an agent that natively integrates with the function calling capabilities of large language models. So we will start and begin with setting up the API key. So after we have completed importing this open API key, we'll import nest SNCO and we'll run this. So for now we are using the MetaGPT paper as the two previous lessons. So we will now set up the function calling agent, and we are using GPT 3.5 Turbo as discussed before, and we are mentioning the temperature is equal to 0. So let's run this. So here, then we import the function calling agent worker from Lambda index and also the agent runner. And for the function calling agent worker, we pass two tools, the vector tools as well as the summary tool. We also pass the LLM and set the verbose equal to true to look at the intermediate outputs. So here basically we are going to ask the first question. Tell me about the agent roles in MetaGPT and then how they communicate with each other. So let's give this as a question. So if we look at the output now, we see that the agent is able to break down this overall question into steps. The first part is asking about the agent roles and the MetaGPT, and it calls the summary tools to answer this question. So now let's look at the content of the first page. So this is the printing the first source model, and we are taking the metadata mode is equal to 1 because we want metadata from each of the responses. So this allows you to, for instance, inspect the content of the first source node that's retrieved. This is the first paper we have given, and here we are using the agent.chat for the first time. The question is about the evaluation of the datasets used. So we will run this. It may take some time to generate. So here if you see, it is basically added user memory about the message, tell me about the evaluation datasets used, and it is calling the function, the summary tool MetaGPT with arguments input it is taking. The evaluation datasets used in MetaGPT include the human eval, it is giving the correct response, and even the LLM responses. The evaluation datasets used in MetaGPT include the human eval, MVP, and software development. So, we are going to see the next question. So instead of query, we will do agent.chat. The first question was about evaluation. It is about the results over the above datasets. So let's run this. Now basically you will see an example of this ability to maintain the conversational history because we will ask a follow-up question. So these are basically separated: calling function, function output, and the LLM response. The function output and the LLM response must be same. So we will start by defining our agent again through the function calling agent and as well as the agent runner setup. So then we started using the low level API. We'll create a task object over here and user query. Then we'll start running through steps for even injecting our own. So here we are even passing the agent worker through this agent runner function. So now let's start with executing a particular step of this task. We are using the same lesson as we have used in MetaGPT, and let's see this. The question is, tell me about the agent roles in MetaGPT and then how they communicate with each other. So I'll give this input. And then let's try a single step of the task. We'll call a .run step task .task id and we'll run this. So it is basically executing and it has added user memory, and there's one calling function that is summary tool MetaGPT with arguments. It is basically taking one input and the agent roles in the MetaGPT. The function output is the agent roles in MetaGPT include the product manager. It is basically giving the output and it is even correct. So previously we can see that it calls the summary tool with the input agent roles and MetaGPT, which is the very first part of this question, and then it stops there. So here in the completed steps, when we inspect the logs and the output of the agent, we see that the first part was actually executed. So we call the agent that completed steps of the task ID, and we are able to look at the number completed for the task. So let's now move on to see the upcoming steps of the task. So now we can also look at the upcoming steps. We can do this through agent to get upcoming steps. Again, if we see the output, we pass the task, that our task ID, and to the agent, and we are able to print out the number of upcoming steps for the task. Now basically we will move on to run the next two steps and actually try and drafting the user input. And here are the next two steps. We can see that we have added that to our user memory, and the next call is how agents actually share information and they can actually give back the response. So the function output is agents in MetaGPT share information through a structured communication protocol. This is basically taken as an input how agents share information in MetaGPT, and this is basically what they have returned as a response. So this is basically the last step and we will run this. So here we are directly getting the LLM response, and it is basically agents in MetaGPT share information through a structured communication protocol. So the overall work is done over here and we just need to return one final step to synthesize the answer. Now to double check that, we can see that we are able to get back the answer about how agents in MetaGPT share information, and it is the last step. Now the last step is finalizing this agent and passing the task ID through this, and we'll run and then print the response. And we'll run this. Now to finalize it, we will perform the final step, and in the next lesson we will show you how to build an agent over multiple documents. So we'll start with setting up the OpenAPI key. We'll run this. And the next, here we will import the nest SNCO, and then the first task is to set up our function calling agent over the 3 papers. So we do this by combining the vector summary tools by each document into a list and passing it to the agent so that the agent actually has 6 tools in total. So here we have downloaded 3 papers from the Clear. This includes MetaGPT for the last time, and it also includes the long loader as well as self-RAG. Next, we'll convert each paper into a tool. So this is basically a helper function, gap-doc tools, which automatically builds both a vector and an index tool as well as a summary index tool over a given paper, and the vector tool performs the vector search and the summary tool performs summarization of the entire document. So for each paper we are getting back both vectors and summary tools. So see, it's generated and we got the 3 tools for 3 papers. Then next we will simplify get these tools in a flat list. So we'll run this. Next here, we are defining 3.5 Turbo from OpenAI and LLM as of our own choice. We'll run this. So now, if we quickly take a look at the number of the tools that are going to be passed to the agent, we will get 6. Because we have 3 papers and 2 tools for each paper, a factory and a summary tool. So let's check. Length of the initial tools. Yeah, 6. So it's giving the right answer. So the next step is to construct our overall agent worker, and it includes all the 6 tools as well as the LLM that we pass out. And we are able to ask questions across these documents or within a single document. So here now we run the code. So for now, let's ask a question about give me a summary of both the self-RAG and the long loader. So let's run this. So it's given added user message to the memory, given a summary of both self-RAG and long loader. Calling function of the output, it is about self-RAG. Function output is about long loader. So it's nice. So we have got the answer that one of the evil data sets used is feature 19 test plate. We are able to look at the evil results for our long haul models. So see the response, okay? We'll print it. Print str and response. Run this. Here are the summaries of the self-RAG and the long loader. It is given a summary. So let's move on to the next question. So here, this code defines the URLs and the papers. The URLs list contains about 11 links to the research papers in the PDF format from the Open Review website, while the papers list consists of corresponding file names that likely represent the downloaded versions of these papers. So each URL in the URLs list maps to a specific file name in the papers list, suggesting that these names might be used to save the downloaded files. So this setup can be useful for automating the downloading process, keeping track of the files, or referencing papers by their assigned names. So we'll run this. Now, this is here to process a list of research papers by actually extracting the specific tools for each document using the getDoc tools function. It begins by importing the getDoc tools from the utils module and the path from the pathlib for the handling file names. An empty directory, the paper to tools directory, is initialized to store the mapping of each paper to its respective tools. The code then iterates through the papers list, printing a message to indicate which paper is being processed. For each paper, it calls the getDoc tools, passing the paper's file's name and its file name without .pdf extension, that would be so this function returns 2 tools: a vector tool likely for converting into embeddings for the NLP task and everything, and the summary tool which might generate the summaries of the paper. So these tools are then stored in the dictionary with the paper file name as the key and the tools as the value. So this setup enables efficient document processing, allowing for easy access to the vectorized representations and summaries of each research paper. So it's generating all the outputs. So now we'll move on. So this code creates a list called the all tools that collects all the tools from the paper to tools dictionary for every paper in the paper's list. So it uses a nested list comprehension, which means it goes through each paper in the papers, retrieves its associated tools, a list of the two tools stored in the paper to two tools dictionary paper, and adds each tool to all the tools. So as a result, all tools become a single list containing all the vector and the summary tools from every paper, rather than keeping them grouped by paper. So this approach makes it easy to access and process all the tools together instead of dealing with them paper by paper. Now, after that is done, this code actually creates an object-based index and retriever for the tools stored in all tools using the vector stored index from the llama index code library that is imported from. So the object index from objects function takes all the tools and organizes them in a searchable index. The index, the index underscore CLS is equal to vector store index. This argument specifies that the indexing method should use a vector based retrieval only, meaning each tool will be converted into a vector representation for efficient searching. So this setup allows quick retrieval of relevant tools based on similarity searches, making it useful for the tasks like finding related tools based on the user queries. So we'll run this. So now this code, that's object retriever is equal to object index as retriever, similarity top k is equal to 3, is creating a retriever object from the object index, which likely represents an index collection of data such as the documents or embeddings. So the asRetriever method converts this index into a retriever, allowing it to fetch relevant results based on similarity. The parameter of similarity top k equal to 3 ensures that when a query is made, the retriever will return the top 3 most similar results based on their relevance. So this is useful in applications like the search engines, chatbots, or recommendation systems, where retrieving the most relevant information is very important. So here the tools equal to object retriever dot retrieve is asking the retriever, that is object retriever, to find the relevant information related to the given query. So the retriever searches through the index data and retrieves the most relevant results based on the similarity. Since object retriever was configured to return the top 3 similar matches, it will return up to the 3 pieces of relevant information. The retrieved results are then stored in the tools variable, which can be used for further processing, such as displaying the information to the user or using it as an AI model. So this process is commonly used in the AI-driven search systems, chatbots, and question answering applications to fetch the relevant data efficiently. Now, let's access the metadata of the third retrieved result from the tools. So we'll write tools, and within third bracket we'll write to and dot metadata, and we'll run this. So this code tools.metadata is accessing the metadata of the third retrieved result from the tools list. Since stores the results returned by the object retriever, each item in the tools contains both the retriever content and the additional metadata. So metadata typically includes the extra information such as the source, timestamp, author, or document ID, or other attributes that describe the retrieved data. So as we have known, we'll move on. So now we are setting up an AI-powered agent that can answer questions based on the retrieval information from a collection of papers. So first it imports the function calling agent worker and the agent runner from llama index core agent. Then it creates an agent worker using the function calling agent worker from the tools, which takes the object retriever as a tool for retrieving relevant information, and LLM to process and generate responses. The system prompt ensures that the agent relies on the retrieved data instead of the prior knowledge. The verbose is equal to true. Setting enables detailed logging, helping to debug or track how the agent retrieves and processes data. So finally, agent is equal to agent runner. wraps the worker inside the agent runner, making it easier to manage and execute the agent's tasks. So this setup basically allows the agent to intelligently retrieve and generate answers based on the predefined knowledge base, making it useful for research, document analysis, and question answering applications. So we'll better run this. So this code is making the AI agent answer a query about the evaluation dataset used in the MetaGPT and how it compares to the SWE bench. So the query function sends this question to the agent, which then retrieves relevant information using the object retriever and processes the response using the large language model. The retrieved and the generated response is stored in the response variable. Finally, we are printing the response, converts the response into a string and displays it. So this allows the AI agent to provide a well-structured answer based on the available documents, ensuring an informed comparison between the two datasets. So it has started generating the response. And then the last step is making the AI agent analyze and compare the two research papers, that is the long LORA and the loft queue. The query function sends a detailed question, making the agent to first analyze the approach used in each paper and then compare and contrast them. So the agent retrieves relevant information using the object retriever and processes the response using the language model. So the generated response is stored in the response variable. Finally, the retrieved and analyzed answer, if you run this, can be printed or used further. So this setup helps in extracting the insights from the research papers efficiently, making it useful for the academic research, technical analysis, and AI-driven summarization. So down the line, let's conclude this course. So guys, throughout this journey of building the Agentic RAG applications, we have explored how to enhance AI's ability to retrieve, process, and reason through complex informations dynamically. We started with an introduction to understand why agentic reasoning is important in retrieval-augmented generation and how it improves AI's ability to handle diverse queries effectively. We then explored the routed query engine, which helps the direct queries to the right sources, making retrieval more efficient. Moving forward, we implemented the tool calling, enabling AI agents to interact with the extract tools and enhance their decision-making capabilities beyond simple text generation. Now, the next crucial step was constructing an agent reasoning cycle, where we developed a system that allows the AI to process information iteratively, improving its responses based on new insights. Finally, we created a multi-document agent which enables the system to pull and synthesize information from multiple sources, ensuring more comprehensive and accurate results. Through both detailed explanations and hands-on demos, we saw how these components come together to form an intelligent agentic RAG system capable of making decisions, retrieving relevant information, and interacting with tools to enhance its functionality. The potential of agentic RAG is vast, from personalized AI assistants to automated research tools and context-aware decision-making systems. So by mastering these techniques, you are now equipped to build and refine your own intelligent AI applications, taking retrieval-augmented AI to new heights. As AI continues to evolve, integrating reasoning, retrieval, and the tool interaction will be a key to developing more capable, autonomous, and adaptive systems. Now it's time to take what you have learned and experiment with building your own agentic RAG solutions to push the boundaries of AI. So guys, congratulations on completing the Building Agentic RAG Applications course. You have taken a major step towards mastering the AI-driven retrieval and reasoning systems. Now it's time to put your knowledge into action, experiment with agentic RAG, refine your agent's decision-making abilities, and explore the innovative ways to enhance the automation and the contextual understanding. Keep pushing the boundaries of AI and making the most of what agentic RAG has to offer. Happy coding, guys, and thank you for being a part of this journey.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.